Hello friends, welcome to the abstract algebra class. In this class, we will prove a theorem. It is class 26. Let us state the theorem. Let H be a non-empty complex of G, the necessary and sufficient condition. It means if and only if for H to be a subgroup of G is A comma B belongs to H implies A into B inverse also belongs to H. Where B inverse is inverse of B in G. We explained the theorem here. Let us prove the theorem. Prove. Let G be a group and H be a non-empty complex of G. It is given in the theorem. G be a group and H be a non-empty complex of G, that is H is a non-empty subset of G. Complex means subset. If a set be subset of another set, the first set is complex of second set. We have to prove that H is a subgroup of G. If and only if A comma B belongs to H, it is implies A into B inverse also belongs to H. According definition, according giving in the statement, where B inverse is inverse of B in G. Once again, we have to prove, we aim to prove that H is a subgroup of G if and only if A comma B belongs to H implies A into B inverse belongs to H, where B inverse is inverse of B in G. Suppose H is a subgroup of G. We now suppose first one here. H is a subgroup of G. We prove second part of the theorem. Suppose H is a subgroup of G. Therefore, H is itself a group with respect to same binary operation in G. Here, when we say H is a subgroup of G, G is a group, H is also a subgroup of G. Therefore, H is itself is a group with respect to binary operation which giving in the G. So H is a group. So we can say A comma B belongs to H implies A comma B inverse also belongs to H. Here, A belongs to H, A inverse also belongs to H, B belongs to H, B inverse also belongs to H, implies A comma B inverse also belongs to H. Because H is a group, implies closure axiom holds, so A into B inverse also belongs to H. Therefore, if A B belongs to H, implies A into B inverse also belongs to H. Converse. Suppose the condition holds. Suppose H is a non-empty subset of G, satisfies the condition A comma B belongs to H. Implies A into B inverse also belongs to H. It is relation 1. We now prove. We suppose that this condition holds. Then we have to prove that H is a subgroup of G. It is our goal for which we have to prove that. Let A comma A belongs to H implies inverse A inverse. Oh, sorry. It is A inverse. A. And instead of A, we put it A. B, we put it A, B. Instead of B, we put A. A into B inverse, A inverse belongs to H. Here in equation 1, we replace B by A. Implies A into A inverse. The result will be E belongs to H. Therefore, identity element exists in H. One condition hold. We now prove that H is a subgroup. Then H should satisfy 4 axioms: closure, identity, inverse, and associative axiom. First one, identity axiom hold. A comma A belongs to H. belongs to H, A belongs to H, implies A into A inverse belongs to H, implies A into A inverse will become A inverse belongs to H. Therefore, every element of H has inverse in H. Second one, inverse axiom hold. Let A comma B belongs to H implies A comma, when A comma B belongs to H, A comma B inverse also belongs to H, implies here when A comma B belongs to H implies A into B inverse also belongs to H. Here A comma B inverse belongs to H implies A into B inverse whole inverse belongs to H. Or equation 1 implies A into B belongs to H. B inverse whole inverse will be B. Therefore, A comma B belongs to H implies A into B belongs to H. This implies H satisfies closure axiom. Number 3, closure axiom hold. We know that H is a subset of G. All elements of H are elements of G. Since every element of G satisfy associative axiom, therefore elements of H also satisfy associative axiom. Here, associative axiom. Therefore H, so number 4, associative axiom also hold. Therefore H is itself a group and H subset of G, therefore H is a subgroup of G. Hence H is a subgroup of G, which is given theorem. If H is a subgroup of G, if and only if A into B inverse also belongs to H. For all AB belongs to H. Hence proof. Thank you.